Mi fa grande piacere essere qui con voi. Infatti io sono venuto nel 2001 in Italia, a Roma, primi 2 anni, e dopo a Torino, lavoro in Telecom Italia, ma prima io sono stato professore a Belgrado. Io sono ingegnere di elettronica, infatti, ma ho sempre fatto matematica anche in ricerca. Io ho insegnato matematica e crittografia a Belgrado. Sono stato anche 4 anni in Brisbane, University of Technology, là, insegnando crittografia, facendo ricerca. E anche sono stato 1 anno e mezzo a Cornell University in America. Mi fa sempre piacere parlare anche per studenti. Infatti si può dire che io sono un controesempio al fuga dei cervelli. Io sono venuto in Italia per stare in Italia perché l'Italia è bellissima e io ho cittadinanza adesso. Comunque il mio italiano non è così buono come inglese. Anche l'argomento di oggi, tutti usano terminologia dall'inglese. Se mi permettete, io spero che mi permettiate passare all'inglese. Voi potete continuare a pensare e fare domande in italiano. Comunque io anche posso rispondere in italiano, ma io ho anche avuto qualche slide da prima in inglese. Okay, very good. So we switch to English now. So the topic of the day is attribute-based encryption and attribute-based digital signatures. And it's not so much mathematics. So it is, formula, elliptic curves, and so on. Because this is where what the pure research gives, because you need technical stuff to apply things. But the focus of the talk is about basic concepts. In this area, it's not so easy to understand, in fact, the concept, what's going on behind. And about some practical aspects, use cases, applications. So this is the objective. Before I pass to the main topic, I would like to provide some general context for the area. So I will say a few words about data security, about data privacy, and about advanced cryptography, because this is the point here of the talk, is advanced cryptography, not basic. Because there are many more things in cryptography than just the basic cryptography. So I have some experience. I worked while being employed for Telecom Italia, because Telecom Italia is a partner of EIT. EIT is European Institute for Innovation and Technology. So I worked there. I led as the leader of the Privacy, Security and Trust Action Line for 3.5 years. So this is where we plan. In fact, in EIT, we planned to promote business there, to promote projects that give rise directly to products and services, 1-year projects. So this is where my interest in business originated. Then after that, in the last year or so, 2 years, I've been the chairman of the NGMN Security Competence Team. So we have a team of experts in security. NGMN is Next Generation Mobile Networks Alliance. So now we are working on 5G, so on the security of 5G. So there are very interesting challenges there. But today I'm not going to talk about these challenges in 5G, but it's related partially when I talk about privacy. So privacy is a very important aspect in future networks. Okay, so let's start with data security. You know that how many dimensions are there to security? How many basic features? What would you say? What do we need to protect? The first one is confidentiality. So data should be, that's the property of data that should be intelligible only to desired entities. So data should be intelligible only to desired entities. How do we achieve this? In practice, so we can use classical crypto, not advanced crypto. So we use encryption, so various kinds of encryption. What is the second dimension? Yeah, it's data integrity. So data, so this is another property. So data should be received or retrieved in original form. It means that if data is received, you should be able to detect that the data is original or not. But of course, enemies or active attackers can always change data. So the best you can hope for is to, in that case, to detect that it is changed. You cannot prevent the attacker. But then there is yet another property which is very important and is becoming critical, in fact, in digital world. That's data availability, right? So data should be available on request. If it's not available, because it is very, very complex, in fact, to achieve that, because you need redundant, basically, resources. So it is costly. Or the service providers just make business continuity agreements with technology providers, and so they should guarantee that under some conditions. For example, in case of nuclear war, nobody guarantees. But in principle, if you don't have data available, generally, to a massive scale, we talk about even the phenomenon of digital desert. So this is very critical of the future in digital worlds. You need to make sure that the data is available. So it is not easy to, and it might be costly to achieve that. Is that all? Or there is some other important property? So it is part, yes, you are right, but it is part of data integrity, in fact. So data integrity is achieved either by symmetric techniques, so it's MACs, famous message authentication codes. So they're based on the secret key exchange between the originator and the receiver. But in that case, you don't have data, no repudiation. So also by digital signatures, if you want, so it should be asymmetric. The key used for signing is only known to one entity. So this is digital signatures. There is yet another property that is related to data integrity. It is entity authentication and identification. Identification is about involving some identity attributes there. So in that case, you in fact need to verify the integrity of identity attributes of entities that communicate to each other. So it can be persons, organizations, things, and in real time. So you need to prevent so-called replay attacks. So it is related to data integrity. It is related in terms of data. But mind one very important fact here. There is also here one dimension that is not only data. You need to verify the identity attributes. You cannot do everything online. You cannot send a copy of your ID online and that's it. You verify your identity. You need to appear in person, possibly with some other, like passport, identity. So physical identification. This is why it is very important to also emphasize this as a separate property, because you need to verify the identity attributes there. So this is, I already said. So for the remote authentication, you use authentication protocols. And then, of course, not everyone in the digital world should verify physical properties. One verifies, and it's trusted by others. It generates digital signatures, so-called certificates, and then the others verify the certificates. So this is the way physical verification is done. But at the end, so there is one entity that should do the verification there. So that's very important. And then for that, you need to step out of the digital world if it's physical attributes. A few words about data privacy. So there are several dimensions to data privacy. The first one is control. So in fact, the user should be able to fully control usage of sensitive data during the whole life cycle. So it includes personal data, but we take it in a general context, so data and metadata. In the general context, also including industrial secrets and so on. So it is generally achieved via user consent. So for the privacy policy should be transparent, user-friendly, and so on. Of course, this is the main problem in the current world, because they are not so. After the introduction of GDPR, we just need to click wherever we visit websites, click, 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 non-stop click, and that's it. So it's not informed user consent. We need to improve that in principle, but that's not the point of the talk. So users should control their data. The second one is security. So data needs to be protected. So data needs to be securely collected, transmitted, stored, processed, shared, and deleted. So it's not privacy, it's not only about confidentiality, it's also about integrity, availability, the right to delete, and so on. Right to delete, by the way, in digital world is never easy, because that's still under debate, whether the users, if they leave traces, in some cases public traces willingly, do they have the right to delete? So that's not generally accepted. So they should ask for deletion, but in fact somebody else in practice decides. So some balance is needed there. And when we are talking about metadata, it's basically the identity attributes, most importantly. If we protect the confidentiality of identity attributes, we talk about anonymity. So anonymity is an important dimension. When we store sensitive data like medical data in database, you typically separate, it's required by law also, identities from data. Because this is what is critical if you associate identities with some data. Whereas, of course, data itself can also lead to identities. This is called traceability. So anonymity, the first property is untraceability. You should not be able to recover the identities. But even if you are not able to recover the identities, you can link different sessions, different data to the same user. You don't know the identity, but you know it's the same. If you collect enough data, possibly you can then recover the identity. So that's another important property, it's unlinkability. So untraceability and unlinkability. And then the way you treat data, ideally, should be according to the Minimality Principle. So, because you need to reveal, in order to get some application or service, you need to reveal your data. But in this sense, according to the Minimality Principle, sensitive data should be disclosed to a minimum possible extent for a minimum period of time, only to entities authorized by the user and to be used only for purposes authorized by the user. So this is ideal privacy. Whether we achieve that or not in practice, it's up to you to make your mind. So the point here is there are important business opportunities here for privacy, because currently privacy is not very well protected. And then in order to promote business in this area, you need some, say, properties of the users. So you need to work on the users. So what would you say, what are the basic properties here to make business out of privacy? The first one, so there are, say, 3 properties that come to my mind now. The first one is that the user should be aware of the importance of privacy, of the need to, and of the value of sensitive data, need to protect and the value. So it's raising awareness. Many people, especially the youngsters, the age like 15 to 30, 35, they don't care about privacy generally. But it can be important because you leave your traces in the digital world even if you are young, and then later it may be important. What is the second condition for business. The service providers, the technology providers should give opportunity, should give a chance to users to opt for privacy. If they provide technology without any privacy there, and they dominate, you know, this winner takes all. That's the dominating paradigm in digital world. You control all the world as Amazon, Google, and then you offer products without privacy. So this is not good for business, for privacy. Are there any such products that you are aware? Where in fact you don't have privacy features. Privacy is the first one, is about control. So control can be implemented by users. Because, for example, if you deal with user profiling and so users in fact should decide on the profile, not others. So that's quite possible. But there are new products by Google and Amazon now, smart assistants at home. And they don't provide privacy features because they know everything about you, connected all the time, so you can switch them off, but only mechanically, most of them, so not by voice and so on. So you don't know what sort of profile is. They do very many useful things for you. Connecting to devices, searching for information. I don't know if you have seen such a smart assistant. So in that case, I don't think that these big technology providers or service providers give chance the users, because they don't apply privacy by design there. And what is the third one? That's the most important one for business. Of course, we can look for now for new business models, how to exploit this privacy. The most important one is that the users should be willing to pay for privacy. Otherwise, we are spoiled. We get so much information, so many services for free. But these big guys, they are doing a really good job, like Google and others, because they provide at least so much information to us immediately. Of course, they select the information, but anyway, so we should be critical of whatever we get from the internet. When we talk about data privacy, it's important to reconcile data privacy with lawful interception, so with lawful cyber surveillance and investigation. But lawful means targeted, so basically it's done for either investigating cyber crimes, some attacks, cyber attacks, tracking, whatever, or for investigating physical crimes in the physical world, so you need to have access to data. But it's strictly under conditions specified by law. So this is okay, but then there is, for example, trade-off between anonymity and accountability. So if everybody is anonymous, it's not easy to do this. So there is, but generally there is no trade-off between, so this was my main point as the action line leader that was controversial. There is no trade-off between cyber or data privacy in cyberspace and data security. It's about the same thing. So it's, when you think about that, you cannot justify access to data by not encrypting data, because this is very critical for lawful interception. Do we protect the data? We'll have millions, hundreds of millions of sensors in 5G. We would like to protect by design this, not to leave only to the applications. And then we would like also end-to-end encryption, maybe between machine and so on, that there are no users involved. And we need privacy by design for that. It's not easy. It's not easy with encryption. We'll say a few words afterwards about that, how to reconcile encryption with lawful interception. One way of reconciling is don't use encryption at all. But that's not very good, for example, for sensors and all other sensitive devices, because then also you open the data to unlawful access. So this is, and then how you reconcile. It's not easy. In fact, one way or the other, you need some sort of storage of the session keys. So it's key escrow, but it can be done in a nice way with secret sharing, threshold crypto, and so on. So there is this issue here. And then if you overreact, say, overdo things with surveillance, you end up with mass surveillance, mass cyber surveillance. And then when you, in fact, associate to massive quantities of data the identity attributes, you get not only user profiling, but citizen profiling. And then if you have such a situation, massive or mass cyber surveillance and citizen profiling, then you violate fundamental human rights. So the main point here is that if you don't have privacy, you don't have freedom, because people, if they know that there are entities in the world who know everything about them, what they do in the digital world, for example, they don't have real freedom to make these free decisions, so, because they are afraid. So this is the point that was raised by Snowden. So this is very important for our digital future to have in mind. And then apart from these basic crypto techniques that I already mentioned when talking about data security, we have many advanced crypto techniques, advanced cryptography for data privacy or for data protection. So let me mention a few things here, which can be important also for this series of seminars, because they can be also important for making business, coming up, designing new services and products. The first one is secret sharing. It enables it to avoid single points of trust and failure. So you split secret sensitive data at least among two entities. You know, for example, if you have a string of bits defining a secret key of 128 bits, for example, you don't want to share to store that key at a single place, but you pick two agents, two computers, and store pieces. So it's shares of the key. How would you do that? 128 bits, how would you store securely at two places? Anyone has an idea? You divide in 64 and 64, and that's it. That's a possibility, but it's bad, because 64 bits reveal 64 bits about the key. You would like the shares not to reveal any information about the key. And how that's possible? There are many sophisticated techniques because you deal with the authorized users. It's related to this talk, in fact. Authorized subsets or subsets of users that should be able to reconstruct the key. Others should not get any information about the key. How would you divide 128 bits into shares in order to achieve this property? It is something, yeah. So you basically generate a random string of 128 bits and give to one server. And then you XOR that string with the secret key and give to the other. So each piece is perfectly masked by the same random information, but they individually do not get any information. When they join their shares, they just do the XOR and recover the key. Anyway, so secret sharing is very important. In fact, you can have so-called secret sharing schemes for many different access structures. For example, one famous scheme is threshold scheme, K out of N. So it means you have N, say, entities, and then you give the shares to N entities in such a way that any K or more from their shares, when they join their shares, can recover the key. But any less than K do not have any information about the key. So it provides both secrecy and robustness, because you can allow some persons or servers not to function at all because you need only k of them. You don't need all of them, all n of them. And then any k, less than k of them do not, if they're compromised better by money, for example, bribe, they don't get any information. Then there is secure multi-party computation. It enables joint computation of functions without disclosing own data. So that sounds impossible. You compute function on data that is not known, in fact. But so there are protocols for this. The point is, instead of giving data, you give masked data. And then you apply secret sharing and whatever, how to compute, to do computations on masked data. Or you can, instead of mask, you can use encryption, in fact, also. Then there is one yet more important. It is practical homomorphic encryption. There is simple, there is fully is relates to universal computations with at least 2 operations. It enables processing of encrypted data, for example, in the cloud. So it's connected directly to ideal privacy in terms of confidentiality. So you give encrypted data and to the cloud, for example, and the cloud computes the function on encrypted data without ever knowing the real data. Provides you the encryption back, and only you, so it's asymmetric, can recover the result. Apart from that, you can have also verifiable computation. You verify that the result is correct. And in fact, up until 5 years ago, there were predictions that it would never be practical. Now it's not the case. I had in the action line, I had some projects, a couple of projects, pointing out with some tricks that in fact fully homomorphic encryption can be practical even for things in Internet of Things. The only feature that you need is long ciphertext, so it's expansion of data, but that's doable. So from the computation point, you can do in fact also fully homomorphic. Then privacy preserving profiling. So using a combination of these other techniques, you can in fact compute profiles without revealing user data. So this is the basic privacy-aware profiling relates to hiding the identities. So it's pseudonymization and data aggregation. So aggregated data, so to avoid traceability. But you can do much more with secure multi-party computation, fully homomorphic, and so on. Because user profiling is a very important property nowadays for business. So this is how you pay for these free services and free data. You pay by yourself. You are the product, by your data. So if you don't want to pay, then basically you must reveal something. So this is, some service providers are offering now services with privacies, but you need to pay for it. So then there is this anonymity protocols. For example, anonymous authentication and signatures. And then to satisfy lawful interception or cyber investigation, possibly with revocable anonymity under specified conditions, possibly coupled with secret sharing. One example is anonymous credentials, so attribute-based credentials. That's very related to this talk also, attribute-based credentials for privacy. So what would you generally say what anonymous authentication means? So basically authenticate yourself, but it's anonymous. For example, it's related to group membership. So you authenticate yourself that you are a member of some group, for example, member of Parliament National. You release a statement. Everybody can verify that you are authentic, so you are authentically member of Parliament, but your identity is perfectly concealed. So this is These attribute-based signatures also provide this anonymity property that we'll talk about. And then there is attribute-based encryption. So this is the topic of today's talk. It enables data sharing by applying, for example, that's the main application, by applying access policies, so access policies for data on encrypted data in a flexible, very flexible way. So I'll talk about that today. There is searchable encryption, search of encrypted data, and there is end-to-end encryption, as I said, possibly with key escrow combined with secret sharing and threshold crypto for lawful interception. So end-to-end encryption is very important. And before 2016, before the WhatsApp end-to-end encryption, you would have very rarely found end-to-end encryption in the real world. But WhatsApp made it really world scale, so it is like more than 1 billion. But the problem with WhatsApp is that it's not so transparent, and the problem is that, in fact, you back up your data, even if you transmit it in one to other part, in the other, like smartphone. In fully end-to-end secure way, so only the keys are stored at the two ends. The problem with end-to-end encryption, you need to make sure that the data is also stored in each endpoint device securely, because basically we store our conversations in the device. And then you store it also encrypted. So this is what also is provided by WhatsApp. It's encrypted inside, like Apple phones. And then the point is, if this data that is backed up in your phone is secure or not. And then it's not only about implementation. You can, in fact, enable data sharing among different apps. For example, you can enable data sharing within Facebook app and WhatsApp. And then basically all your secure end-to-end conversations are available to Facebook. And then you can do all sorts of things, so it's certainly not end-to-end encryption. And in fact, this is what they did after Facebook bought WhatsApp. They enabled, initially there was no data sharing. For practical reasons, they enabled data sharing by apps. So that's possible now. They say they don't do that, but it is possible. So this is it's very critical to obtain security. Another point is how you generate the keys there. Are they really unpredictable and so on? So we spent quite some time on the introduction. I hope it was interesting, I mean, for the context, but maybe the talk will be a little bit longer. It seems, I don't know, what is the timing now? Okay, yeah. So we continue with the introduction. So now we switch to the topic, so it's about attributes. Attributes, we go quickly through this. We deal with attributes here. Attribute is any verifiable physical or logical property of any entity, so not only persons, also things, services, whatever, which itself is described as a string of characters or bits. So you can describe it by a sentence. You can also associate indexes, index them, and then this is how you treat effectively, technically with attributes. And then, so for example, attributes can relate to age, role, education, profession, expertise. So it's much more general. They can relate both to persons and to data. So the type of data, type of digital content, financial data, but also identifiers. So identifiers are also type of attributes. Identity typically uniquely specifies, as that's a definition you can find somewhere, an entity in a group of entities. So it's a set of identity attributes that uniquely specify. Here, an entity. Here, attributes are taken more generally. So you can consider any property. And then attributes need to be verified. So at some point, if it's physical properties, there should be some entity verifying the attributes, and then it issues the certificates, and then the others are using certificates. So this is how it works. Somebody should verify the attributes. And then you can use attributes for access control, access to data, for example. This is what we are dealing here. Access to files, to broadcasted multimedia content, to medical records. You store medical records in servers, and then you should control access based on attributes. But this is what we are going to talk about. Also to various data generated by meters, sensors in IoT, and so on. So this is the topic, attribute-based access control, access to data. We are going to deal with binary attributes. So it's the attributes that specify a property that is either satisfied or not. So you can associate a Boolean variable to each attribute. So it's just mathematically a Boolean variable that has value 1 or 0. If it's 1, if it's satisfied attribute. If it's 0, it's not satisfied. Then you can also deal with, in principle, more generally with numerical attributes, but then they need to be expressed for the techniques here that are used in attribute-based encryption as binary attributes. So this is in fact a tricky point here, because this is why I mentioned here in red generalizations to integer variables. We are going to deal only with binary variables here. If you deal with an integer variable, you need to represent integer variables in terms of binary. For example, if there is a set of integer values, to each value associate a particular binary attribute. So if it's a large number of values, it's complex. So this is important topic for further investigations, how to generalize the existing techniques to non-binary attributes. There are some generalizations, but basically this is it. We are going to deal with binary attributes. So now what is access policy or access structure? So it's a Boolean function. It's a predicate over binary attributes. So access is allowed if the access policy has value 1, given the values of attributes. And then, so you provide access, they allow access. And access is denied if the value is 0. Typically, we deal with monotone structures, access structures. As Boolean functions, they can be expressed in terms and, or, and threshold gates. But also, in some applications, we deal with non-monotone structures, so they include NOT gates also. And we are interested here to apply access policies to very fine-grained Boolean functions, so to enable fine-grained access control. So to generalize, for example, to any Boolean function. But typically, monotone is if one Boolean function is satisfied for some attributes. If you increase the number of satisfied attributes, so a superset, the function will maintain value 1. So this is monotone. So if it's satisfied for 2 attributes, it will be satisfied also for 3 attributes, including these 2. Okay, and then for access to sensitive data, I give 3 examples here of sensitive data. Sensitive database files stored on untrusted servers. For example, personal medical records, IoT data produced by smart meter sensors or personal variables, financial data. So this is all data stored in servers. You need to, so they are sensitive. So you don't want, if the server is untrusted, you want to store them in encrypted form. Then pay-per-view multimedia content, for example, sent out in broadcast. Multimedia, so movies, only the users that are subscribed should have access. Audit log data for various systems to be accessed by authorized entities. So they serve for forensics or for examining the status of the system. Only authorized entities should have access to audit log data. So data attributes can relate both to data itself or like this type of multimedia content or other metadata. or type of log data, type of document, and so on. So it is data, or they can also be associated with entities having access to data. Access policies can include both types of attributes, those related to entities and those related to data. So classically, what would you do to protect this data in order to satisfy some access policy? You segment data in particular segments. At each segment you encrypt. You typically apply okay, so I'll talk about that later. You typically apply symmetric key encryption for that, and then you give the keys to entities that satisfy the access policy. So this is the main. Attribute-based encryption will enable generalization and more flexible management and avoid problems with key management. But before we pass to that, let me give some examples related to access policies. So the first one, so we are dealing with attributes with binary variables. We have three binary variables, A, B, and C. So access policy A or B and C is satisfied if A is equal to 1 or B equal to, or both B and C equal to 1. So you understand this. So this is the access policy, whether it's satisfied or not. There is this threshold gate that I mentioned. So threshold 2 out of 4 means that if at least 2 attributes, input attributes, have value 1, any of them, any 2 of them, so the output will be 1. So this is threshold function of A, B, C, and D. It's implemented by threshold. You can implement both AND gate and OR gate by threshold. Yes, so threshold gate is general, threshold gate. Then for personal medical records, regarding applications, for personal medical records, PMRs, they can be labeled by types of medical data, so related to different diseases, for example, and expertise and or affiliation of medical practitioners that should have access to data, that are allowed to have access to data. So access policy defines which practitioners can access given data with some attributes. For pay-per-view broadcast content that I already mentioned, it is labeled by metadata describing features of the content, such as genre, time of production, so year, month, date, episode, scenes, actors, directors. So these are the attributes associated with the content. And then access policy for a given user defines subscription package for that user, so the user paid for, and then that's the access policy is defined in terms of attributes. So which movies, in fact, for example, the user can access in broadcast, because the movies will be encrypted. They will be encrypted by symmetric key encryption, and then in order to decrypt, you need access to that symmetric key. And then, so this is what you need to do. And then for audit log, you have database entries labeled and indexed by metadata as attributes. This metadata can relate, so it depends on the type of the database, maybe to identities, to times, to type of data there, and so on. And the access policy, for example, for forensic analysis is defined over this metadata. For example, if you store NetFlow logs, they include these features of the IP packets. So you store the payload encrypted, and then these attributes. So this is metadata, and then the access policy is defined in terms of attributes. Attributes, in this case, the metadata like source and destination IP address, port numbers related to applications, and so on. So the users that should investigate, examine log data should satisfy with their credentials these access policies. Otherwise, they cannot access the data. So classically, if you use classical encryption, you need data keys. So to encrypt data by some key and apply symmetric key encryption for it. And then you need to distribute data keys to authorized users depending on their attributes and also attributes of the data. So depending on access policies. In principle, in order to distribute online, so remotely, the data keys, you need some underlying infrastructure. So it's either secret key or public key. Typically, it's public key infrastructure. So basically, if you want to distribute one data key with which some multimedia content is encrypted, only to particular users, then you check the access policies and only select these users, and then you encrypt with their public keys the data key and send to each user. You apply different encryption with the respective public key, and then only that user can get the data key. So this is typical of what you do in the classical case. And then even in broadcast, so if you say wirelessly broadcast the content to users, for each user you need a separate encryption by its public key. So the communication complexity is linear in the number of users. And then each time you change content, you change the keys, you need to repeat the same thing. So this is classical encryption. This is what we are going to avoid by attribute-based encryption. Another problem is dynamic policies. So whenever you change, that I already mentioned, so whenever you change the content or access policy, you need to redistribute the data keys to users according to their policy. So you need to check the access policy and redistribute. So this is not very practical. So this is what can be avoided by attribute-based encryption. You don't encrypt the data key for each user separately. And then you don't need to, each time you change access policy, you need to redistribute the keys. So this is the main thing of attribute-based encryption. So far, it was introduction. Now we can, in the remaining time, we can talk about attribute-based encryption. So if attribute-based encryption is used for real-time transmission of encrypted data keys to users, then each data key needs to be encrypted only once by using a global unique public key, and each user satisfying the access policy can decrypt by using its own private decryption key. So there is one public key, multiplicity of private decryption keys. So that's different to the classical scenario where also the private key is unique. So multiplicity, and somehow these attributes or access policies are embedded in either encryption or decryption keys, and then in the decryption function or the decryption keys. So we have different types of attribute-based encryption then. And then only those satisfying the policy should be able to recover the data key. So this is tricky. And it might seem impossible, but in fact there are practical techniques to achieve that. And then this encryption by attribute-based encryption, essentially, it consists in masking the data key. So we want to transmit 128-bit secret key which encrypts some data to users. And then basically, how do you do this by attribute-based encryption? You mask that key by a random mask there. Another 128 bits. And only the users that are authorized with the access policies satisfied can recover that mask. So basically, you share the mask with all the users that are authorized. Others that are not authorized cannot obtain any information, nothing about it. And then the size of encrypted data and communication complexity in this case are linear in the number of attributes. not users. So when you study the techniques, you see that the linearity is in the number of attributes. You can get very significant savings if you don't deal with identity attributes. If you deal with identity attributes, then you don't get the saving because the attributes are identities of users, so the number of attributes is the same as the number of users. But in that case, what is the saving for identity? You use only one public key for encryption and known identities. So that's much easier. You don't need public key certificates and public key infrastructure. So this is because identity attributes are particular attributes. And then another point is that you can flexibly change in the encryption either access policy or attributes, and you don't have to retransmit the data keys. So attributes and access policies are built in combined encryption and decryption functions, so that only the users having the right private decryption keys which satisfy the access policies can decrypt and hence obtain the data key and the data. So there is inherent flexibility allowing dynamic access policies and or attributes. So this is the main property. So let me say a few words about the attribute-based encryption itself. So in this ABE system, ABE, there is a single public encryption key PK and multiple private decryption keys DK that are given to the users. In the setup, the key management server, KMS, generates for itself the public key and its secret master key, MK. So it's not only to the KMS. And then it verifies, so as I said, you need to verify the attributes. It verifies the validity of user attributes, either directly or by verifying user attribute certificates. And then by using the public key and this master key generates randomized private decryption keys, DK of users. It can be done initially or in real time. And distributes them to users of a protected channel. So you need to do this in the setting only. And you need, if you want online, you need, for that, you need secure channels. And then you can switch off this entity, and then the users can communicate. You don't need online servers for this. So there are two types of attribute-based encryption. Key policy ABE, KPAB, ABE. Access policies in this case are built in private decryption keys, so it is user-specific action policy. So each user has its own action policy. And attribute set, so it's a set of satisfied attributes, is specified in the encryption. So the encryptor, each time, it has flexibility to change the attribute set. But the access policies for users are fixed. And they are embedded in the private decryption keys of the users. You cannot change that. But the encryptor can each time change the attributes that are relevant. So this is the typical use case for multimedia broadcast. Because the attributes that you can change in encryption depends on the data. They depend on the data, so the type of multimedia content. Whereas the users have their decryption keys with built-in access policy depending on the subscription package that they paid for. So only some of them will be able to recover the key and read if they paid for that. So this is KPABE is especially convenient for the case where the attributes relate to data that you distribute to users. There is the other type is ciphertext policy ABE, CPAB. Attribute sets in this case are built in private decryption keys, so each user has a set of attributes possibly related to the user. So in this case, it's the attributes related to users. Not necessarily. It can be also related to type of, for example, medical data you have access to. So it can be a mixture. And then, so this is more flexible ciphertext policy. Each time you encrypt, you can totally change the global access policy for all the users. So for each, this is ideally suited to personal medical records. So you change type of record, then you can change access policy, and then only some medical practitioners can have access to data, read the data. So this ciphertext policy is more flexible because you can each time change access policy, and then you just do the encryption and send the encrypted data to all the users. So only those that are authorized can recover. Others don't have any information. Basically, when you try to decrypt, they obtain information from the program. It's not possible to decrypt. It's not possible. So only if they satisfy the policy, they can, and you can specify each time a new policy. So you don't have to redistribute the keys and nothing. So it's the same keys there. You change policy. So this is why it's very powerful. So this is what I already said in KPABE. Decryption with decryption key works if and only if an attribute set built in ciphertext satisfies the access policy built-in decryption key. So attribute set can vary with each encryption. This is what I said. You can change multimedia content and vary the relevant attributes there. In ciphertext policy, decryption works with DK if and only if an access policy built in ciphertext is satisfied by the attribute set built in DK. This attribute set built in the decryption key is always the same, but the encryptor can change the access policy each time. And everything is randomized, so basically you can just, you don't have to redistribute the keys there. Encryption time and ciphertext size are linear in the number of attributes. So this is the general property that I said. And then you use randomized, so there is for DK, when the KMS generates the keys, decryption keys, they are randomized. So two users, for example, could have the same attribute set or the same access policies, but they are given totally different keys because the decay is randomized. So this is the basis of the collusion resistance. This is what makes the design of these schemes difficult, this collusion resistance property. It means that the authorized users cannot join their information, their decryption keys, to come up with a new key for some new access policy or new attribute set. So this is tricky to prove that your scheme, so this is more precisely expressed here. And then also the encryption itself is randomized. So each time you encrypt the same message, you obtain something totally random that you cannot distinguish from other messages. This is important for privacy, for unlinkability. I will at the end talk about that. So this is what I already explained here. We used two colors here, so it is this dark red for KP, key policy, the rosy one for ciphertext policy. So there is data, there are attributes related to data, so with this subscript D, and then in the red, the encryptor in the red case, so it's key policy, can use some attributes, so related to data and also related in principle to user, and encrypt. And then, so this is this case, and then there is the access policy related to user. So in the decryption case, it uses in this dark red one the access policy related to the user. And then it can decrypt if and only if this policy is satisfied. Otherwise, it doesn't have access to data, to the key, so it cannot recover nothing. And then in the other case, in fact, you in the encryption, you can build in or embed any access policy. So it's global. Here it's local, related to the user, like subscription packages I talked about. And then here is global, so each time you can change that. And the user uses the attributes, so they are embedded in the decryption key, and then applies this policy. If it's satisfied, it can decrypt, otherwise not. So this is very quickly, so it is much more flexible, this ciphertext policy, because each time you can totally change global access policy. And now you can verify for yourself, because time is passing, this example. So for example, for personal medical record, you use embedded policy. A, it's the attribute saying doctor with some name, because you like some famous doctor to ask for opinion. Then there is the attribute B, is doctor with some specialization. There is attribute C, doctor with at least 10 years of practice, so you're interested in experienced doctor. D is doctor employed at hospital 1, because this hospital is very nice, for example, a very nice criteria, environment, and whatever. So these are the relevant attributes. And then you like to encrypt your medical record with this policy. A or B and C or D. It makes sense if you read it. And then, so this is one Boolean function of 4 variables. And then you can verify yourself that these subsets of attributes, because this is ciphertext policy AB, so the keys have embedded subsets of attributes, the users. So these ones can all decrypt. Why? Because if you substitute these values for 1, the access policy will be 1. So this is the criterion. And on the other hand, these ones here cannot decrypt. For example, B and F, because if you substitute B to be equal to 1, then there is this variable F, which is not reflected in the policy there. So you cannot, or only C, because you need, if you substitute, okay, so for example, let's consider BF. So if you substitute B for 1, then you have A or C or D. So this is not necessarily 1. So it should be 1 in all the cases, for all the attributes that are there. And similarly for key policy AB, so it's some broadcast content, you can have attributes A, it's genre, B is some actor 1, C is actor 2, D is director 1, and production year. And then your subscription package can reflect some access policy, for example, this one. The access policy is what I had here, so it's all right. So these are the attributes. They are built in the encryption. And then the access policies associated with users can decrypt the following ones. Because if you substitute these attributes here, in this access policy, they will be equal to 1. Otherwise, these access policies are not necessarily always 1, and they cannot decrypt. Because, for example, for this one, you need also some other attribute F to be satisfied, and it's not. So you substitute these attributes to be all equal to 1. So this is in the encryption, and then you see if these access policies associated with users are equal to 1 or not. So this is. So there are practical aspects. Is the size of the public key. So typically, there is this universe of possible attributes U, and the public key originally in the first papers was linear in the total number of possible attributes. That might not be, so even if you choose only 3 attributes for encryption, if there is a total set of 100 attributes, the public key should reflect all of them. So that's not practical. Then there are so-called large universe constructions, when in fact the size of the public key is linear in the number of attributes that you effectively use, or even with some hash function constructions, it can be fixed in size. So that's very practical, that's very relevant for practical applications. So this is key policy. In ciphertext policy also PK size can be fixed or linear. As I said, KP is more suited to data attributes, while CP is more suited to user attributes, but you can use combinations. So there is an issue of revocation here. Revocation of the keys, revocation of the attributes. You can deal with revocation, for example, by using expiry times of decryption keys, and then you use the expiry time as an attribute here. But the point is that you should understand, because you can compare the expiry time of the decryption key and the current time of the encryption, because it should be bigger than the... you cannot compare directly, it's not binary attributes. So basically in the encryption you need to ask for there's one method, for the expiry time, and then you compare yourself in the encryption, and then don't send encryption at all if it's not satisfied. So this is one way. Revocation of attributes is more complicated. So if there are 2 entities having the same attributes, you want to remove only one set or whatever. So this is an issue. And then, okay, so of course, this is a general property, the bottom line of cryptography. If you give your keys to other entities, they can always decrypt. So it's up to the users to keep private their keys. And then, so for signatures, it's related, it's only one slide, it's related to non-repudiation. So basically you use private signing keys and public verification keys. But in attribute-based signature scheme, so you use a sort of ciphertext policy scenario. An entity with a private signing key, so it's known only to that entity, can generate a valid signature with an access policy embedded in the signature. So each time, like in CP, you change access policy. So it can generate a valid signature if and only if the attribute set that is embedded in the signing key, so it's like in CP, satisfies this access policy. And then the user, the signature, reveals only the access policy, so not the identity, nothing. So it's related to anonymity. So this is why this, and then in fact, there are schemes. So you use global public key for verification. You only reveal about the user the policy. So this is anonymity. So the policy, not the attributes. So it is unlinkability in that sense. And it would be ideal because the strategy here is similar to ciphertext policy. In fact, to use the same keys as in CP scheme, and that's possible. So this is called ABES. So you can use then the same keys as in ABE, CP ABE, for these signatures. So it's for, but now you don't use the decryption key for signing. For decryption, you use it for signing. And then the verification is by the single public key. And then it is interesting that there are ABES schemes that can be generated from anonymous credentials, attribute-based credentials. And attribute-based credentials, by the way, are interesting because you can deal with integer variables there. So what is this attribute-based credential? Just one sentence here. So you have, unlike the public key certificate that binds your identity to some private public key, and then you know only in the classical sense, the private key there. Attribute-based credentials or anonymous credentials enable unlinkable signatures, so it is sort of anonymous authentication. You can prove based on that credential. So it's not only the classical private key that can be verified by public key. It is more. So there are special techniques how to do that. Issuer gives you that credential. So each time when you authenticate yourself, you can prove to the verifier that your attributes satisfy some predicate, some Boolean function. And each time unlinkable totally. And then you can also, these predicates can involve integer variables. So it's very powerful. These are anonymous credentials for anonymity. You can use them for attribute-based signatures also. So I guess we can skip the mathematical hints here. So basically you need to apply these schemes based on some mathematics. And then, so there are research papers. There are already many research papers about ABE, ciphertext policy, key policy. It is a generalization of identity-based encryption, and it is made possible by efficiently computable bilinear maps. That's the only slide with mathematics here. So and then, so you use, what is this bilinear map? You have two cyclic multiplicative groups G and H of prime order P and some generator G. Cyclic means that each element can be expressed as a power of G. And then, so both of them have the same order. And then you map pairs of elements from G into H. In order to satisfy this property, and satisfy this property for this bilinear map. If this property is satisfied, it's called bilinear map. Of course, this is a necessary condition, otherwise you will always have the result 1. So the mapping of any two elements from G, so X to the A and Y to the B, is in fact the mapping of the element's action Y raised to H by B. So this is the property. Then you can base bilinear maps on elliptic curve groups, and then they are called elliptic curve pairings. And then you have to deal with large cyclic groups of elliptic curve groups. So this is all known, the algorithms how to do that. For elliptic curves, typically we use additive notation, so it's not multiplication, so it's not like this here. It's when you deal with additive, the exponentiation. Instead of exponentiation, you deal with point multiplication, because instead of multiplying one element many times, you add that element many times. So then it's a scalar multiplication. And then the operations there are finite field operations. So the elliptic curves are defined over finite fields. The operations in elliptic curve groups are finite field operations. So this is complex. And there is this also operation of pairing, which is even more complex. So this is related to how you compute things efficiently. And then, because the computations, remember, are somehow linear in the number of attributes that you use. Then, this is, I would like to make this point, if you design an algorithm in cryptography nowadays, you should deal with relative security proofs. So you should reduce the security of that complex protocol to some primitive, to some problem expressed in a more compact form. So this is all what you do, in fact. In this case, this is the so-called decisional bilinear Diffie-Hellman assumption. We don't have time, of course, to explain this, but you prove if this problem is difficult to solve, then this some scheme, proposed scheme, is secure even with collusion, respect to collusion resistance. So this is, and then you can do that formally. So this is a formal theoretical proof. It's called security reduction, but it's not real security proof. People use the wrong terminology. They call security proofs. It's just security reduction proof to some other problem. In this case, this is it. So you need to, if you have a nice idea about the new scheme, you need to provide the security, you need to study how to do these things. So you need to be expert in these proofs. And then how the main point is to embed, in fact, access policies or access structures in ciphertext or private decryption keys. This is where you use secret sharing, for example. So this can be tricky. And then in terms of practice, encryption time can be on the order of magnitude inefficient implementations, like 1 milliseconds per attribute. So if you have 100 attributes, it's 100 milliseconds. So it can be practical. You can, in fact, build practical applications, even for mobile. Then these elliptic curve operations for mobile use binary elliptic curves over binary field. They can be implemented faster than the others. So this is doable. And then there is just the basic articles. So KP was introduced in this paper 2006 by Goyal, Pandey, and others. It is for access structures expressed in terms of trees of threshold gates. So it's a tree of a threshold gate. And also for more general access structures that are also monotone, that correspond to linear secret sharing schemes. It's called monotone span programs, it's equivalent. And then for a general Boolean function, you can check this paper. So they proposed a scheme for a general access structure. And then for the key policy, for the ciphertext policy is the other article. Some of the authors like Waters and Sahai are the same. It's 2007. So you can check the literature. It's very interesting. And in fact, they're already using these schemes for storing and sharing personal medical records in US. And they propose to use this for broadcast. I don't know if they succeeded to do that, but in principle it's doable. You can think of new applications. So this is an important area for business. So I have only 2 slides more, very quickly, in few minutes. So this is what we did in Telecom Italia. So it's related to mobile systems, to 4G and 5G. So there is this famous IMSI piece of information that is stored on your mobile, on your SIM card. Did you hear about that, IMSI, or no? So in the mobile systems, 2G, 3G, 4G, in the future 5G, it will be the same. We use secret key, shared secret key, pre-shared secret key infrastructure. So the mobile operators have secret keys and subscribers have the same secret keys. And this is how they communicate to each other. And each operator has a database of these secret keys. And then you authenticate yourself as a valid subscriber by some protocol, ACA authentication protocol, based on pre-shared secret key. It will be the same in 5G. So it's not public key or something, it's pre-shared. So basically you need to trust as a subscriber the mobile operator. You entrust the mobile operator with the keys. And then the point is to establish the connection by using this authentication protocol. The mobile operator needs to find the right key for you. There are many millions of users. So IMSI is the piece of information that defines uniquely a subscriber. So you send IMSI in the clear form, and then your operator can find the right key for you and then establish the connection and so on. If you are in roaming, you do that with a visited network. You send the IMSI to visited network. Visited network sends IMSI to the home network. Home network finds in the database the key and establishes the connection. The problem was that IMSI was sent. You cannot easily directly encrypt IMSI because mobile operator needs clear IMSI to find the right entry in the database. So far, up until 4G, the IMSI was sent in the clear. It means that the user, the attackers, by so-called IMSI catchers, can in fact monitor the traffic in an area and record all the IMSIs there. So initially, when you establish the connection, you send your IMSI. Afterwards, if you lose the connection, you resend your IMSI. So it enables tracking of users, moving the user, how the users move, so it's not privacy aware. So in 5G, it's going to be changed. So the IMSI can be, or will be encrypted. Of course, it's up to, this is always the case. It's almost always the case, except for signaling information. All these standards need to be implemented by the equipment, but the operator or user decide whether to use them or not. So it depends on the regulations in a country. But it will be supported. Encryption of IMSI will be supported in 5G. So IMSI contains the country code, the operator code. So these two uniquely specify the operator and the information related to the user. So this is unique. Altogether, this is globally unique. And then, then there is this technical specification. Now, currently it's release 15 that's completed of 5G. It is done by 3GPP. It mandates the support of the encryption of only this part here. And then this is transmitted in the clear. So the home network receives this in the clear, country code, operator code, and this part encrypted. And it is encrypted by the public key of the home network. So this is the trick. And then because the visited network sees these two codes for routing, it says to the home network, and the home network decrypts. And it's the same as before. But the point is, for lawful interception, also the visited network should know the IMSI, because these policies for lawful interception are expressed in terms of IMSI. And then, so basically, after decryption, the home network, not only does it establish the connection, it should also send IMSI in the clear form to the visited network. So this is how it's done. It's simplified, and it provides only partial privacy, because you can track the users in some area by these two components. If there are very few users in some area, it gives some information about the user. So it's not ideal privacy. So is it possible to encrypt all of the data, all of the IMSI? It is possible. You can use, so it is IMSI encryption by ABE, but not only ABE, it is possible to use classical public key encryption, but then you can encrypt by the public key of the visited network. And then the visited network can decrypt and then send to the home network and the same thing. The problem is, if you encrypt classically, then the user equipment, the smartphones, should deal with certificates of all these public key certificates of the visited networks, and that's messy. So this is a problem. There are also some other problems. So we proposed in Telecom Italia to use attribute-based encryption, a variant that is related to identity-based encryption, in fact, with expiry time also. And it is published, in fact, in a mobile. So this is a standard of ETSI, TC Cyber, for applications of attribute-based encryption. If you are interested, you can check there are other use cases. One use case is mobile case, and it's exactly the scheme that we proposed in Telecom Italia. And then also in 3GPP, we propose that scheme also for 3GPP, but for simplicity, so there is so far only the technical report, not technical specification, because only that method from the previous slide made it to be a standard currently, because it's simplified instead of attribute-based encryption. Because I didn't want to complicate things, one thing with attribute-based encryption is that you need this KMS, Key Management Server. So in this scenario, so this server is sending the decryption keys to the users. So you may speculate that it knows the decryption keys of the users. So this is, and then in this case, it is interoperated if you are going to use ABE interoperator, so you need some trust framework. This is the limitation, but you can deal with that. So just a few more lines and I am done for today. So how it works, this method that we proposed. Upon request, each mobile operator receives the decryption key from KMS with embedded. So it is like a scenario with ciphertext policy, so it's embedded attributes. The attributes in the key are the country code, the operator code, and the expiry time. So an operator gets that decryption key. And then securely. Then the smartphone or user equipment, this is what is already happening now. It receives in broadcast MCC and MNC of the visited network. So this is what is already now present. And then it should also, that's a modification, requires to send the expiry time and uses them as an attribute for the encryption. So in this case, because it's essentially identity attributes, it doesn't matter if you call it KP or CP, it's the attributes. So you use it as an attribute for attribute-based encryption. So the attribute is MCC, MNC, and the expiry time of the visited network. So you use that in encryption, and then we use a large universe construction for fixed size PK, because in this case, the attributes is the number of operators. The PK can be prohibitively large if you don't use the large universe construction for fixed size PK, so it's fixed size PK. And by the way the ABE works, only the attribute, only the mobile operator with these attributes that are used in the encryption will be able to recover. So that is the visited network. And the main point here it's related to the trust of the KMS is that this KMS can be implemented with some schemes that we propose totally distributedly. So in that case, it is trustworthy. We use secret sharing and threshold crypto. So basically, you don't store this master key at any place. You don't generate a distributed, this private decryption key at any place. Everything is distributed. So this is how you spread trust and you get things more trustworthy. So I'm sorry that I took more time, but this is it. I used to be a professor a long time ago. Of course, in Italy, I cannot be a professor because Italy is very close to foreign. You know, the university system is very close to foreigners. Now I'm not foreigner, but anyway, so I am of age now. But sometimes I like to talk, so sorry for a little bit longer, but I will be very happy to answer any questions. You can ask questions in Italian. I can choose whether to answer in Italian or English.